Section 8.4, Vectors. So, background information. We measure some quantities using only their magnitudes. Now I have this word here called scalars. Scalars is just a word for a non-vector. And so some specific examples of some quantities we measure using only their magnitudes are time, length, and mass. If you think about the way we measure them, you just see a number and that's it. Now, on the other hand, we measure some quantities with their magnitudes and their direction. And so specifically some of those quantities are displacement, velocity, and force. Now, all three of these, if we're going to actually talk about these things, the moment we say them, we mean that they have a magnitude and a direction. So, once we have magnitude and direction, we have described what's called a vector. Now, we need to have a way to represent vectors, and so a vector in the plane is just a directed line segment. And then we're going to say that two vectors are equivalent if they have the same magnitude and the same direction. Once again, magnitude means the exact same thing as length. Alright, so let's consider a vector drawn from point A to point B. Point A is going to be what we call the initial point. Point B is called the terminal point. That is, it begins at A, it ends at B. It can be notated as AB with an arrow over the top, and this is read vector AB. Now, we can also denote vectors using bold-faced lowercase letters, okay? So either you have to have the arrow or you have to have the bold face, and you can interchange them sometimes if you so desire, but recognize that if we're writing things, I don't have a way to make things bold, and so if I write a vector, I need to put the arrow over it all the time. Well, if we look at these four vectors over here, that is vector AB, vector CD, vector OP, and vector V. Now V is already written, but I'm going to write it again just to indicate that if you write it, you need to put the arrow over it. Well, if we look at all of these, I claim that all four of these vectors have the exact same direction and the exact same length. Now, with that direction, the arrows have to point the same direction as well. And so since they're all equivalent, we can say that vector AB is equal to vector CD, is equal to vector OP, and is equal to vector V. Note that when using the arrow vector notation, the terminal point must be on the arrow side. That just helps tell you where the initial point and the terminal point are. Now, since we have this idea, let's show that vectors U and vector OR in our image here are equivalent. And so afterwards you can show yourself that W is equivalent to those as well. But we're just going to do U and O. U and OR. Now, if I want to show that they have the same magnitude, that's just length. And I have a distance formula. Specifically, the distance formula is equal to y sub 2 minus y sub 1 quantity squared plus x sub 2 minus x sub 1 quantity squared. And if I'm trying to figure out direction, well, because we're on a plane and we just have ordered pairs, I claim that we can figure out direction using slope. Recall that the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And so let's figure out what these vectors have as in terms of length and direction. So let's start with vector u. Well, vector u has a distance. The distance is equal to the square root of y sub 2, 4 minus 3 quantity squared plus 2 minus 1 quantity squared. Then we get that this is the square root of 1 squared plus 3 squared. 3 squared. 1 squared is 1, 3 squared is 9, 1 plus 9 is 10, root 10 is the length. Well then, let's check the slope. Slope is just going to be 4 minus 3 divided by 2 minus 1. And I get that's 1 over 3, and so there's our slope. Well, now we need to compare that to vector OR. And so vector OR has a length of the square root of 0 minus 1 quantity squared plus 0 minus 3 quantity squared. So here I get 0 plus 1 is 1 quantity squared is 1 plus minus minus 3 is positive 3, 3 squared is 9, 1 plus 9 is square root of 10. Lengths are the same. Let's check slope. Slope is then going to be 0 minus minus 1 divided by 0 minus minus 3. I get 1/3. Therefore, we have matching slopes, matching lengths. The directions are the same because the arrows are pointing in the same direction, in addition to the lengths being the same and the slopes being the same. Therefore, I can say that vector u is equal to vector OR. And so we have shown that. Now we need to be able to do vector arithmetic. And so the easiest set of arithmetic that we know how to do is addition, and so vector addition is pretty easy. Well, geometrically, if you're trying to add vectors, all you need to do is put the initial point of one vector on the terminal point of the other, and the vector that you get from the initial point of the first vector to the terminal point of the second vector is the addition of those two vectors. And so if you notice in my image, u plus v gives us this vector starting from A to C. The sum of the two vectors is also called the resultant of the two vectors. And so if u is the vector a, b, and v is the vector b, c, then u plus v is the vector ac. Well, this extends a little bit and we get this thing called the parallelogram rule. Essentially, because we can do that picture that we just had, where u could be first and then we tack v on the end of it, you could also do the vector v and tack u on the end of it, and you get the exact same sum. Well, this is useful because what that tells us is that vector addition is commutative. That is, the order in which we add vectors does not matter. Now, I'll go ahead and tell you that vector addition is also associative. That is, if you're adding 3 or more vectors, you just group 2 of them, any 2 of them first, and then you just keep adding. Well, the next piece of arithmetic we need to talk about is this thing called scalar multiplication. And so, when we're dealing with vectors, a real number is just a scalar. So anything that's not a vector, if it's just a real number, it's what we call as a scalar. And so let's assume that alpha is a scalar. Then the scalar multiplication, alpha times the vector v, is defined like this. If the vector a is greater than 0, then the scalar multiplication alpha times the vector v is just the vector whose magnitude is alpha times the magnitude of the vector v, in the same direction as v. And so notice that over here I have an example. If you take the vector v and you let alpha be equal to 2 and you multiply 2 times v, then what happens? Well, because alpha is positive, the arrow stays pointing in the same direction. But then all that changes is the magnitude, and so multiplying times a scalar of 2 literally doubles the length of that vector, and that's exactly what's happened in this image. Vector v times 2 is double the length. Now, let's suppose that alpha is negative. If we have a scalar that's negative, then when you multiply it, the magnitude multiplication is the same, except that you use the absolute value, and then you put the arrow in the opposite direction. And so notice that if I take the vector v and I multiply it times the scalar -1, it takes the exact same vector v and just puts the arrow in the opposite direction. And when we're thinking about forces, this works out really nicely, because if you're going in one direction and then you turn completely around and you go the other direction, that vector is negative. Also note that there does exist multiplication times 0, and so if you have a scalar alpha is equal to 0 and a vector v is equal to 0, then alpha times the vector v, this should be a bold 0, so it's actually the 0 vector. And so if the scalar is 0, 0 times a vector gives you the 0 vector. Now that we have scalar multiplication, I claim that vector subtraction is pretty easy. And the reason is that if I have two vectors, v minus w, then what happens is all I have to say is, oh, well, that's the same thing as saying v plus negative w, where you're really thinking about negative w as a negative scalar times w. Well, that negative scalar, or that -1 scalar times w, just points it in the opposite direction. And so geometrically, if you're trying to find sums, well, just draw w, and then you tack the vector v onto w, and wherever you finish from where you started, that is the sum v plus w. Needs an arrow? Great. Well, the trick here is that if you want to do vector subtraction, you can do very similar things. V minus w is really just v plus negative w, and so in the parallelogram it will help you geometrically represent this. We can flip w to get negative w here, right? There's negative w. And then just take the vector v and add negative w to it, and going from the starting location of v to the terminal location of negative w is my vector subtraction v minus w. And so now we understand geometrically how to represent vector subtraction. One thing I didn't mention, but I'm actually practicing, is that vectors just have to have a direction and a magnitude. Once you deal with the direction and the magnitude, you can really move them anywhere in our plane and they still have the exact same meaning. Direction and magnitude are what's important, which is why I can move all these things around like I'm doing. Okay, so let's do some vector arithmetic. Let's say that I take the scalar 0 times the vector v. Well, what do we get? We get the vector 0. Okay, and it is a vector. Well then, what happens if I take 1 multiplied times the vector v? Nothing happens because 1 just keeps the vector as is, and so I just get the vector v. Well then, if I take negative 1 and multiply times the vector v, that is really the negative vector v, or the vector pointing in the opposite direction from the initial vector v. If I have two scalars, alpha plus beta times the vector v, then vectors do distribute over scalars. And so this is the same thing as the scalar alpha times the vector v plus the scalar beta times the vector v. Also, scalars will distribute over vector addition, and so that is alpha times the vector v plus alpha times the vector w. And then we do have associativity that works with scalars here, and so if I have alpha times beta times the vector v, that's the same thing as alpha times beta times the vector v. Now let's consider how we're going to do arithmetic with vectors geometrically. And so recall that I said we can just kind of move these around in the plane. What matters is that we keep them the same length and direction before we do the arithmetic. And so if I were to take that arrow that I just drew on top of the vector v, and I were to then multiply it times 2, well, what happens? It's literally going to double in length. And so this is the vector 2v. Well, if I want to add the vectors v and w, remember that I can move them around a little bit, so let's draw the vector v. There it is. Then let's just put the initial point of w on the terminal point of v. There we have v, then w. Well, then v plus w is just going from the initial point of v to the terminal point of w, and we get the vector v plus w. For v minus w, same idea. I'm going to take the vector v, and I just moved it around to make life easier for me. Then remember that I'm going to really think of this as v plus the negative vector w. And so these should both have arrows on them. And so then I just need to put the arrow on the other end of the vector w, and then put its new initial point on the terminal point of v, and then recognize that this is actually indicative of v minus w. And so geometrically, that's how we do vector arithmetic. Each one of these directed line segments that are in red are the vector arithmetic. Okay, so we're not just going to work with vectors geometrically, we're going to work with them as their number parts too, but to get there we need to have a different representation. And so we're going to talk about position vectors. And so the vector v, whose initial point is at the origin and whose terminal point is at the point AB in the standard position, is in what we call standard position, and is referred to as a position vector. Specifically, position vectors are going to be written, you can of course still use the boldface letters or the letters with the arrows, but when we're trying to deal with, and these are going to be called components of a vector, when we want to deal with the position vector of a vector, that is, we need to indicate the x part, which is really a here, and the y part, which is b here. Now, if you're not noticing, the reason that we're talking about these things in trig is because you're really going to be able to represent them using right triangles, and so that's why they come up now. So this vector v, being equal to the component vector ab, is considered to be in what's called component form of the vector v, meaning specifically, like I said, that a is the horizontal length and b is the vertical length. Now, once you have position vectors, there's an additional way that we could represent those position vectors. And so sometimes we use specifically what's called a unit vector. And remember, unit is just a math term for 1. And so a unit vector is a vector with length 1. And so specifically, we're going to use I and j notation. And so I is going to be the unit vector in the direction of the x-axis, and j is going to be the unit vector in direction of the y-axis. And so if I have the vector v in component form as ab, then if I want to write this using I and j, I just write that as a times the position vector 1, 0 plus b times the position vector 0, 1. Then I can write as a times I, the vector I, plus b times the vector j. You may also hear these i's and j's referred to as I hat and j hat, but that's often because when we write these vectors, we can't boldface them, and so they have a hat on them. I hat and j hat. So just so you know that terminology, the vector I, the vector j, I hat, j hat are respectively the same thing. So now what we want to do is we are told that the vector v has an initial point k and a terminal point L. We want to write the vector v in the form ai plus bj. That is, find its position vector. So, first off, what can we do? Well, if you wanted to draw it, you are more than welcome to. And so if I were to sketch this, -4, -3, -4, -3 is right here. And then 1, 5, just trying to get us an image to keep us in line. And so then this vector, KL, looks like this. This is the vector KL. Well, but if we want to write it in its component form, or that is find the position vector, then what we need to do is we need to pick it up and we need to shift it to right here, keep the same direction, keep the same magnitude. Well, how can we do that? Well, specifically, I just need to figure out what is the x length and what is the y length, or specifically the horizontal and the vertical length. And so consider that if I have this information here, and I have the ordered pair for L being 1, 5, and I have the ordered pair for K being -4, -3, all I need to do is find the x distance, and I need to find the y distance. But to find the x distance, well, that's just the distance between the two numbers. So that's going to be the final minus the initial, or x is going to be equal to 1 minus -4. Okay? 1 minus -4 is 1 plus 4, or 5. Well then, if I want to find the y portion, that's just going to be the difference in the terminal minus initial part, and that's going to be 5 minus -3. 5 minus -3 is 5 plus 3, or 8. And so since we're actually finding the horizontal length and the vertical length, I claim that we have actually found the components of the vector KL. Now, one way to write that is now 5, 8. So this is a position vector. But we could also write in the form, and we were requested to, AI plus BJ, which is then going to be 5I hat plus 8J hat. And so those are the different ways that we can write the position vector, and now we actually know how to find vectors, how to find the position vector given a vector. Now, recall that magnitude is the length of the vector. And so if we have a position vector, v is equal to the components a and b, then we actually write magnitude. Magnitude is going to be written like this. Sometimes, for the record, you may see it written as just absolute value bars, and so it's just going to depend upon the text, but in this text they use double bars. And so the magnitude is really just the a part squared plus the b part squared. So you just square the components and then add them and then take the square root. This is really just a distance formula, considering the fact that AB is the terminal point for a position vector. The initial point for a position vector is the origin 0, 0. And so that's all we have to do to find the magnitude if we know we're working with a position vector. So, given that KL vector that we found earlier, let's find the magnitude. All right? Well, the magnitude of the vector KL is just going to be equal to the square root of 5 squared plus 8 squared. That is the square root of 25 plus 64, which is the square root of 89. And so then, if we can, we do want to try to simplify that square root, but the square root of 89 won't simplify because 89 is a prime. But that is our magnitude. Once again, two vectors are equivalent if they have the same magnitude and the same direction. So for position vectors, this is super easy. That is, if you have the vector u, which in position vector form, its components are u sub 1, u sub 2, and you have vector v, its components are v sub 1 and v sub 2, then the vector u is equal to the vector v if and only if the components are equal. That is, the u1 is equal to v1 and u2 is equal to v2. Now that we have the ability to write position vectors, we can actually deal with that arithmetic that we were talking about earlier more generally rather than just the geometry of it. And so if we want to do scalar multiplication, well, what happens with scalar multiplication? It distributes over the components. And so k times the vector v is equivalent to k times the component v1 and k times the component v2. How does addition work? Well, if you have position vectors, then it's as easy as adding the components. And so the vector u, the vector v, given in these component forms, that means you just add the u1 v1 and you add u2 v2. Subtraction, same idea. You just subtract the components where the subtraction symbol's on the correct vector. If the vector u is the component 6, negative 2, and the vector v is negative 3i hat plus 5j hat, we want to find the following. First off, recognize that I just wrote it in two different ways for you guys so that you could see both representations, but of course you can adjust this. This is then 6i hat minus 2j hat, and this, if you would rather in the component form, is negative 3, 5. And you can work with whichever one you want, but if you use the I hat j hat notation, then you just treat it algebraically where I and j are different variables, and then everything works out like it's supposed to. And so u plus v, that would be 6i hat minus 2j hat plus negative 3i hat plus 5j hat. Then we just combine like terms. The coefficients of I hat, 6 minus 3 is 3i hat, minus 2j plus 5j is plus 3j hat, which of course in component form could be written as 3, 3. Make sure you use those pointy brackets, and so either of these is perfectly fine. Then let's try u minus 6v. So u minus 6v is 6i hat minus 2j hat minus 6 negative 3i hat plus 5j hat. Just distribute that scalar. That's going to give me 6i hat minus 2j hat minus 6 times minus 3 is positive 18i hat. Negative 6 times positive 5 is negative 30j hat. Then we get that this is 6i plus 18i, or 24i, minus 2j minus 30j, that's negative 32j. There's our answer. Of course, if we so desired, we could rewrite that in terms of the component form, that is 24 minus 32 in our pointy brackets. And that's perfectly okay as well. Then 3u plus 4v, 3 times 6i minus 2j plus 4 times negative 3i plus 5j. Distribute our scalars. 3 times 6 is 18i minus 6j minus 12i plus 20j. Then 18i minus 12i, 6i, and then negative 6j plus 20j plus 14j. And so 6i plus 14j, or as component form, 614. Then we need to take the magnitude of 5v minus 2u. Okay, so we're taking the magnitude of 5 times the vector v, where the vector v is negative 3. These double bars a little larger. 5 times negative 3i plus 5j minus 2 times the vector u, which is 6i minus 2j. Then distribute our scalars. This is negative 15i plus 25j minus 12i plus 4j. Combine like terms. We then get that this is the magnitude of negative 27i hat plus 29j hat. Then we're taking the magnitude of this vector, and that's just going to be the square root of the components squared and summed. So that's negative 27 squared plus 29 squared. I get that that's the square root of 729 plus 841, which is then the square root of 1570, and that's our magnitude. Then remember that we talked about unit vectors, but we talked about specific unit vectors, those being I and j, where those were the unit vectors for the x-axis and the y-axis in the positive direction. Well, now what we want to do is we want to find unit vectors for all types. So a vector of magnitude or length 1 is specifically called a unit vector. And the unit circle is made up of unit vectors because the radius of the unit circle is 1. Well, if the vector v is a vector, and that vector is not equal to 0, then 1 divided by the magnitude of v times the vector v, or the vector v divided by that magnitude, is a unit vector in the same direction as v. And so we really just force a scaling down of making that vector be a length 1. And so if we want to find a unit vector that has the same direction as this vector w, where we have these components, well, all I need to do is I need to find the scalar, which is the magnitude of w, and put that under the vector w. So let's first find the magnitude of w. The magnitude of the vector w is the square root of negative 3 squared plus 5 squared, which then gives us the square root of 9 plus 25. And so that means that my magnitude is root 34. Great. Well then, if I take the components and divide it by the scalar, right, because that's really all we're doing, the unit vector is then just negative 3 divided by root 34 and 5 divided by root 34. I claim that this is our unit vector. Now, of course, we could write it in the I and j notation if we desired. That is negative 3 divided by root 34 I hat plus 5 over root 34 j hat. And so either way of writing it, this is specifically our unit vector for w. So now, because we recognize that we're going to have these vectors that just kind of float around in the plane in all kinds of different directions, we need to be able to figure out how to find the direction angle. This is where the trig comes into play. So, recognize that the terminal point of a unit vector in standard position is a point on the unit circle. Specifically, it is the point cosine theta sine theta. Thus, the unit vector can be expressed in component form. That is, the vector u is equal to cosine theta sine theta. Or, if you would rather, as a linear combination of the unit vectors I and j, where u is equal to cosine theta I hat plus sine theta j hat. Well, therefore, for any vector v with magnitude, the magnitude of v, and theta in the direction, and theta is the direction angle between v and I, we get that that vector is equal to the magnitude of the vector v times its components, cosine theta I plus sine theta j. This is identical to what we were looking at with polar coordinates. So, let's say that a ball is thrown with an initial speed of 90 miles per hour in a direction that makes an angle of 30 degrees with the positive x-axis. Alright, so real quick, just to kind of sketch my image, we have a baseball that has an initial speed of 90 miles per hour, and it has a directional angle of theta being equal to 30 degrees. We want to find the ball's position vector in terms of I and j. And then we want to indicate the initial speed in the vertical direction and in the horizontal direction. Well, what are we doing? The vectors, remember, in component form, and I haven't named this vector, so why don't we call this vector vector v. Then we know now that vector v is equal to the magnitude of v times cosine theta times I plus sine theta j hat. Now, recognize that if we weren't using the I and j notation, you would have to have pointing angle brackets to indicate that these are components of a vector, but we're okay with the I and the j notation. So then, from this application problem, I claim we know the magnitude. The initial speed is the magnitude, 90, times, well, we know what theta is, cosine 30 degrees, I hat, plus sine of 30 degrees, j hat. Well, then we can just distribute the 90 and we could calculate this. Our vector is then going to be 90, well, cosine of 30 degrees is root 3 over 2 I hat plus 90 degrees sine of 30 degrees is a half j hat. And so then we get our vector as 45 root 3 j hat root 3 I hat plus 45 j hat. Now the best part is that if somebody was asking us what is the speed in the horizontal direction, we actually have it, right? The x component, or the coefficient of I hat, is the horizontal speed. And the j hat component is the vertical speed. Thus we've done it. And there we are. Now we want to find the direction and the magnitude of the vector v hat being equal to 4i hat minus 4j hat. So, if we want to find direction and magnitude, what do? Well, draw the position vector. Remember that the position vector is, well, recognize that this is 4, negative 4, that is the vector, but that means that the terminal point is the point 4, negative 4. So, 1, 2, 3, 4, negative 4. The terminal point is at 4, negative 4. And so this specifically is my position vector. That is the vector v. So let's start by finding the magnitude of the vector v. Well, the magnitude of the vector v, that's just going to be the square root of the sum of the components squared. And so that is the square root of 4 squared. 4 squared plus negative 4 squared. That's going to be the square root of 16 plus 16. But I'm just going to rewrite that as 2 times 16, because then the square root of 16 is 4, and this is 4 root 2. So now I know that the magnitude of my vector v is 4 root 2. But now we need to find the direction. Now, in general, when we're working with our thetas for this, we're going to find theta between 0 and 360 degrees, or between 0 and 2 pi. But we'll exclude 360, we'll always write it as 0. And so, if I want to find this angle, this is the theta that I actually want. but we need to be a little bit careful, because the way that we're going to find that is by doing what? Well, I recall that tangent of theta is equal to y divided by x, and so if tangent of theta is equal to y divided by x, that's going to be tangent of theta is equal to negative 4 divided by 4, and so that is tangent of theta is equal to negative 1. But then I'm going to take tan inverse of both sides, and when I take tan inverse of negative 1, I get that theta is equal to tan inverse of negative 1, which via the range restrictions for tangent inverse gives me negative 45 degrees. But that's not the answer I want. What I just found was this angle. And so since this is a negative 45 degree angle, I need to find theta. Well, that's just going to be 360 degrees. That's just going to be 360 degrees minus 45 degrees, which is 315 degrees. And so that is the theta, that is the direction, with a magnitude of 4 root 2. Well, then let's find the direction and magnitude of the vector v being negative 11 root 3 plus 11. So I like to sketch them first to keep myself on track. And negative 11 root 3, positive 11, I'm not going to scale it, but it's somewhere over here, where specifically that ordered pair is negative 11 root 3, 11. Wonderful. Well, then let's find the magnitude. So the magnitude of the vector v is the square root of the components squared summed, which is negative 11 root 3 quantity squared plus 11 squared. That is the square root of 121 times 3 plus 121, which is the square root of 363 plus 121, which is then the square root of 484. And so the square root of this is 22. So now I've found my magnitude. Well, then I need to find my theta. But theta is, of course, the theta that I want is this, right? That's the theta that I want. But recognize there's a problem, and that is when I take tangent of theta, I recall that it's y divided by x, or 11 over negative 11 root 3. I then get that tangent of theta is equal to negative 1 over root 3. And then I take tan inverse of both sides, and I get that theta is equal to tan inverse of negative 1 over root 3, which I get to be negative 30 degrees. Now, problem. Negative 30 is this angle, right? And since that's the negative 30 degree angle, I need to find a distance of pi away from that. So I need to add 180 degrees to that. So 180 degrees minus 30 degrees is going to give me 150 degrees. And so I claim that our theta that we want is 150 degrees. And so I'm just using the period of pi to find that other side.